This is a video on the equation for a plane. All we need for this equation is one point in the plane, one known point in the plane, let's call it P0, and the normal. Sometimes these are given, and so if you have these two pieces of information, you can write the equation. Sometimes the normal is not given, in which case you need 3 points in the plane. So we're starting here with the generic point. I'm sorry, this is a point in the plane. And now we say there's some other x, y, and z. In general, it doesn't even have to be in the plane. This is just a generic point. Then we need to write the equation for the generic vector between those points. Let's go back and look at the other picture for a minute. So we're starting off with P0 in the plane, and we write the equation for a position vector. So position vector, you recall, starts at the origin and moves up to this particular point. So the R0 would be x in the I direction, x0, I'm sorry, y0 in the j direction, and z0 in the k direction, where the coordinates of P0 are x0, y0, and z0. Then we have this other point here, which is generic, so its coordinates are x, y, and z. Now the idea is that once we develop this and write a certain equation, then every x, y, and z that satisfies this equation lies in the plane. Right now, it's just a generic x, y, z. So this position vector is z belongs over here on the k. Z is just from the coordinate. And then we construct this, which I'm calling v. So here we have our generic vector between those 2 points. Really, it's a vector between the 2 position vectors to those points. And we said for this point, at this stage, we know the normal. Someone's given us the normal. Well, now, the normal is orthogonal. It's at right angles to the plane. It's right angles to every vector in the plane. So if this vector v lies in the plane, that is, if x, y, and z that's a point in the plane, then the dot product between the normal and this vector will be 0. So this is our test that if for the x, y, z coordinates of that point, they lie in the plane, then the normal and this vector are at right angles. So we'll go ahead and carry out the dot product between the normal and this generic vector and set it equal to 0. Now we rearrange this equation, and here we have the the x, y, z's that we're trying to test. All of these terms are known. The x0, y0, z0 was known to be a point in the plane, and the a, b, c are the components of the normal. That's abbreviated as d. This isn't the only way to write this equation. You have to be a little careful when you're looking at this equation. The other way to write it is to put the d on the other side and write, ax plus by plus cz is equal to d. Basically, it's the same thing with a sign difference. So the difference between this d and that d is sign. Thomas writes it this way, and Stewart writes it this way, I think. So different authors write things in different ways. You just have to be careful when you look at that equation. So here we had one point in the plane and the normal, and from that we wrote an equation. It's sort of interesting. A line has a vector equation, and a line, you needed 2 points. So when you think of a line, you just think of points, and yet here's a vector equation for the line. For the plane, a plane is determined by vectors, and yet the equation for it is scalar. So anyway, that's how that works out. So this is just an example, a point in the plane with coordinates 1, -1, and 3. The normal's given with components 2, 4, and -6. Here's the equation. All it takes is substitution now. And we get the equation for that plane, for the plane that contains this point and has this normal. And every x, y, and z that satisfies this equation lies in the plane. Now if the normal is not available, then instead of 1 point in the normal, 3 points are needed. Now the reason you need 3 points is that with these 3 points you create 2 vectors. You take the 2 vectors, and from that you create the normal. Then you go back and use one of these points and the normal and do just what was done before. So for example, here are 3 points. From these we create position vectors. We take the difference between the position vectors and create 2 vectors in the plane. Their cross product gives us the normal. So here's an example of calculating that normal from those points before. So we have V as 2, 0, -1, and U as 0, 3, -1. We put them in the proper matrix form here and take the determinant. This determinant is very easy. You can just read it off. It's 3, 2, 6. All those zeros were very helpful. So now we have the normal to the plane, and now we just pick a point. So you have 3 choices of points to pick, and you have the normal, and it does not matter which point you pick. Right? And you can go through that exercise. I did that in the written lecture notes that kind of go with this video. So here we have the equation we're looking for. We have the ABCs from the normal that we calculated, and then we pick one of these points. I picked this one, and here's the equation for that plane. If you take these 2 vectors, these 3 points, and you create different vectors, or you take the cross product in a different way, it won't matter at all for the equation for the line. Because look at this. What we're working on is n dot v. So if I took what I created for those 2 vectors, v and u, and ended up with this normal, if I had done it in a different direction, I would have a different normal. The only difference between the 2 would be, this would be minus n dot v, and these are both equal to 0. So multiply by -1, and you get the same equation. Also, the unit normal is not needed. You can use the unit normal if you want, but it's not needed. Unit normal would be n over the magnitude of n, okay, dotted with v equals 0. This is a scalar. You can multiply both sides by it, and you end up again with n dot v equal to 0.